please make sure that you're checking the lab schedule to see when your lab section does lab number 1. Okay, so last day we ended off talking about the structure of the computer and software flow and some of the performance measures that we use to assess computers. Pardon me. Today we're going to do probably a little bit of a review. In 177 we show you number systems and the binary and hexadecimal number systems. We're going to review that today. So we're going to look at number systems again, and then we're going to look at how numbers are basically added and subtracted in a computer using the 2's complement system for signed numbers, and then how floating point numbers are stored in computers. Okay, so some of this is going to be review, and yeah, nothing too crazy. So these are lecture notes 2, which you should be able to find on Canvas. Okay, so let's just first review what we've known for a long time, which is decimal numbers or base 10 numbers. And we've been using that ever since we started taking arithmetic in grade school. And so in the decimal number system, just like in any number system, we have placeholder values, okay? And in the decimal number system, they are based on deci or 10. Okay, so the first or the lowest significant digit in our decimal number has a placeholder value of 1. The next least significant has a placeholder value of 10, and then it just keeps multiplying by 10. So 10 to the 1, 10 to the 2, 10 to the 3, tens, hundreds, thousands, and so on. Okay? And we have, in the decimal number system, we have 10 digits that we can use, 0 to 9. And so the total value of a decimal number is obtained by adding each digit, adding the product of each digit with its placeholder value. So if we're looking at the decimal number 4623, its value, which we know is 4,623, is basically obtained by 4 times 10 to the 3, which gives us 4,000, 6 times 10 to the 2, which gives us 600, 2 times 10 to the 1, 20, and 3 times 10 to the 0, 3 times 1 is 3, and then you add those up to get 4,623. Okay, so the decimal number obviously is just the digits, 4623, and the total value of the decimal number, as we just did, is the sum of the products of each digit by its placeholder value. Okay? Every other number system is basically the same. So binary numbers, in the binary number, binary means 2. We have 2 digits we can work with, 0 and 1. Those are the only 2 digits we can use. And therefore the placeholder values are 2 raised to the power of 0, 1, 2, 3, 4, etc., etc. So our placeholder values are no longer 1, 10s, hundreds, thousands. It's 1, 2s, 4s, 8s. You just keep multiplying by 2. Okay, but the same system or the same process is involved. If, for instance, we wanted to figure out what the value of the binary number 1101 is and express it as a decimal number, because we're so familiar with decimal, we just do the same thing. We take each digit and we multiply it by its placeholder value and add them all up. So if we start here at the most significant digit, 1 times 2 to the 3 is 2 to the 3 is 8. The decimal value 8, so 1 times 8 is 8. So this has this 1 here in the binary number 1101 has the value of 8. This one would have the value of 4. 0, obviously, 0 times 2 is 0, and then 1 times 1 is 1. So you add those up, you get 13, or the binary number 1101. Okay, so binary, all you have to remember is that 1, 2, 4, 8, 16, 32, 64, 128, etc. are the placeholder values. Okay, and same thing, we have a list of binary digits, ones or zeros, and as we showed before, we can calculate what the total value of that binary number is by, again, summing up all the products of the digits by their placeholder values. Okay, and if you ever deal with binary a lot, it's usually worth remembering, for instance, if we look at a 4-bit binary number, it's often good to sort of memorize the binary numbers in ascending order, and there is a pattern. If you start with the least significant bit, it just alternates. All right, the second least significant bit also alternates, but in groups of 2. So it would be 0, 0, 1, 1, 0, 0, 1, 1. And then the next least significant bit, or the second most significant bit, alternates, but in groups of 4, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1. Okay, and then the most significant bit alternates in groups of 8, so that means it would be 4, 5, 6, 7, 8. Okay, so it's often handy when you're dealing with binary numbers if you can write them down in ascending order relatively quickly. So their decimal values then would be 0, 1, 2, 3, 4, 5, 6, 7. That would be 8, 9, etc., etc. Okay, so binary numbers, which you've seen before in 177, and maybe somewhere else already again. Any questions so far about binary? Okay. Excuse me. All right, so how do we convert between decimal and binary? Well, you know, there's a couple of different ways. I typically don't use the method here. I'll talk about this method in a second, but if we are, I guess in this case, we are trying to convert the decimal number 11, and I'll write that 11 sub 10 to show that that's the decimal number 11, not the binary number 1, 1. I just do the sort of old school brute force. I just write down my placeholder values until I've got one bigger than the number I'm trying to convert. And then I say to myself, okay, well, what is the largest placeholder value, 1, 2, 4, 8, 16, that fits into the number that I'm trying to convert, which is 11? Well, that's obviously 8, so I put a 1 there. 11 minus 8 gives me a remainder of 3. So 4 is too big, but 2 would work. And 3 minus 2 gives me 1, and then obviously I need the last one to get me down to a remainder of 0. Okay, so that's the way I do it. You know, it works relatively good for smaller numbers. Bigger numbers, it takes a little bit longer, but that's the way I do it. The alternate way to do it is what's shown here, which is repeatedly dividing your decimal number by 2. Which is the base of the binary number system, and obviously this would work for any number system, decimal to any other number system as well. For instance, hexadecimal, instead of dividing by 2, hexadecimal, as we'll see, the base is 16. So you would divide the decimal number by 16 to convert to hexadecimal. But in this case, we're dividing by 2, pardon me. We're dividing by 2. So we start down here. Here's our decimal number, 1, 1, or 11, I should say. And again, I'm going to put a subscript 10 there to indicate explicitly that that's a decimal number. So 11 divided by 2 is obviously 5 with a remainder of 1. So this first remainder becomes our least significant digit in our binary number. That is going to represent 11. We then divide 5 by 2. Well, 5 divided by 2 is 2, again with a remainder of 1, since 2 times 2 is 4. And so 5 minus 4 gives us another remainder of 1, so that becomes our next least significant digit. 2 divided by 2 is then 1, with a remainder of 0, since 2 goes into itself 1. So this 0 again is the next digit, and then obviously we can't divide 1 by 2 anymore, so that becomes our last binary digit. Okay, so this is an alternate way. Obviously this will, you know, work for any decimal number. You just keep dividing by 2. Your remainders are your binary digits until you get to the end. Any remainder at the end would be your last would be your last binary digit, or your most significant binary digit. Okay? So if you haven't seen that before, that's another easy way of converting from decimal to binary, or decimal to any other number system as well. Okay, so you've probably seen this somewhere before. I know we showed this in 177, so a couple of years ago. These are sort of the four most often used number systems, especially in the computer world. Obviously, everybody's familiar with decimal, or base 10, and we just looked at binary. We also often see octal, and even more so hexadecimal. Octal has base 8, so there's only 8 digits you can use, 0 to 7, and then they start repeating. Hexadecimal has 16 digits, so we use the same 10 digits as decimal, and then we need 6 more, so we start using letters. So A, B, C, D, E, F are the last 6 digits in the hexadecimal number system. All right, so you know, if you haven't seen this before, it's worth taking a look at this for a couple of minutes just to get familiar with it. Okay, we're not going to look at octal so much. It's not used very much anymore. You might still see it every once in a while. Much more common, especially in assembly language programming, is hexadecimal. So we're going to be looking at that in just a moment. All right, some definition, words that you've probably seen before. We know what a byte is, or you have at least have heard the word byte. A byte is basically, or is, 8 bits. Okay, so because the data paths inside of computers can have different widths. Some computers are 32-bit computers, others are 64-bit computers, and maybe even bigger. We have some words for subsets of a word. If we're dealing with an ARM processor, which is what we're going to be learning in lectures, the ARM processors have a 32-bit width for the computer. So that means all the buses, all the data buses in an ARM processor are 32 bits wide. There's 32 separate communication lines, one for each bit. And so that the word in an ARM processor is 32 bits long. So we define those full 32 bits as a word. In a processor that only has 16-bit buses, we would say a word is 16 bits. Okay, so the size of a word, or the number of bits in a word, can vary from computer to computer depending on the data width inside the computer. Okay. Bytes and nibbles, on the other hand, are always the same size no matter what the data width in a computer. A nibble is always a subset of 4, and typically it's the last 4 bits, but it doesn't have to be. Okay, just 4 bits is a nibble, whereas 8 bits is a byte. Okay, so in the ARM processor, one word would consist of 4 bytes and consist of 8 nibbles. Okay, and in all of our figures, when we actually write out a word like this, we typically, pretty much always, we call the bits on the far left-hand side of the word the most significant bits, whereas the bits on the right-hand side the least significant bits. So we can also talk about the most significant byte and then the least significant byte, just to keep things in order. Okay, so nibbles, bytes, and words, and least significant and most significant. Again, if anybody has a question, just stick up your Zoom hand or just call out and I'd be happy to answer. Okay, so far so good. Nothing too crazy. So we looked at binary, and the other number system that we see a lot in assembly language programming is hexadecimal. One reason for that is, or a very significant reason for that is that memory systems these days are very, very large, and therefore the addresses for each location in a memory system are very, very big numbers. Okay, And the convenience or the advantage of using hexadecimal, for instance, to express a memory address, which is what we're going to do all the time. Whenever I draw a memory like this and I give it some addresses, and we already did this in the last lecture where we looked at the software flow as an instruction is being executed, we always use hexadecimal for the addresses. So, and 0x is the indicator that this is a hexadecimal number. So 0x00, 0x01, 0x02, etc., would be the addresses of these individual memory locations in memory. Because there's so many memory locations in modern day memories, the addresses consist of a lot of digits. If we would use decimal numbers, hexadecimal, because it's base 16, its base is bigger than that of decimal, which is base 10, the numbers are more compact. And therefore, it's just a matter of convenience, and we're just lazy. We don't want to write such big numbers, so we use hexadecimal because it means writing fewer digits in that hexadecimal number. Another very convenient reason to use hexadecimal, not so much for memory addresses, but for instance, when we start looking at a particular instruction, an assembly language instruction, we're going to be looking at that a little bit today. It consists of a number of bits, okay? And so it might be some, it will be some combination of ones and zeros, something like that. For instance, that might be the machine language representation for a particular assembly language instruction. And the convenience of hexadecimal is we can write this again in very shorthand notation, a hexadecimal number, simply by dividing this into 1, 2, 3, 4. Oh, I missed by 1, so I'm going to add one more bit there. We can divide this binary number into nibbles, so subsets of 4 bits. And then all we have to do to convert this to hexadecimal is substitute the hexadecimal digit for each nibble. So here's a long number. I can just use this one up here. So here's a long binary number, 01001101. Okay, so this would be a 1, 2, 3, 4, 5, 6, 7, 8 times 8 is 64-bit binary number. So that means writing 64 bits. If we wanted to write that in binary, if we wanted to write it in hexadecimal instead, we just divide it into subsets of 4 bits. So you start at the least significant bit and take the first 4, that first nibble, and you write the corresponding hexadecimal digit that corresponds to this 4-bit binary number. And this 4-bit binary number is equal to the decimal number 15, right? If you add up the placeholder values where there's a 1, well, there's a 1 at every one, so 1, 2, 4, 8. 8 plus 4 plus 2 plus 1 is 15. The next one is obviously 0. The next one, again, you just treat this as a independent 4-bit binary number, so it has placeholder values again of 1, 2, 4, 8. So 1 plus 2 is 3, right? So that gives us 3, and we keep doing that for all of these, okay? And therefore, our binary, or if this is our binary number, our hexadecimal number would be 0x4D6B830F. Okay, so instead of having to write 64 ones and zeros, we can instead write 1, 2, 3, 4, 5, 6, 7, 8 hexadecimal digits. So as I was talking about before, assembly instructions, if we're writing them out on paper, which we'll do during the lecture part of this course, they're typically represented as hexadecimal numbers instead of the full binary number. But if you're given a hexadecimal representation of an instruction, and you want to now see what the different parts of that instruction are, as we'll see in the next lecture or two, then you have to break it down into binary to see what the individual ones and zeros are. But we'll get to that in a bit. Okay, and finally, we can convert a decimal number to hexadecimal, just as we did with binary. So for instance, if we're converting the decimal number 237, we just divide it by 16. So 237 divided by 16 is 14 with a remainder of 13. And therefore, this becomes your least significant digit. Okay, and decimal 13 is the hexadecimal digit D. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. And then this remainder, which can no longer be divided by 16, is your last remainder. And so 14, a decimal value of 14 corresponds to the hexadecimal digit E. Okay, again, the other way you can do it is you can write out the placeholder values, pardon me, of hexadecimal, and do the same thing as I did with binary. Okay, but because these numbers get so big right away, often this is an easier way to do it. Okay, so that's hexadecimal. Any questions about binary, hexadecimal, etc.? Okay, so more or less review. All right, well, the other thing we need to talk about is because computers only store ones and zeros, so far we've talked about how we can store numbers, obviously as a binary number, in a computer. Well, what about characters? A, B, C, the digits 1, 2, punctuation marks, commas, periods, etc. How do we store those in a computer? When you type a character on your keyboard, how is that stored in the computer? Well, the oldest and maybe best known way is with what we call an ASCII code, the American Standard Code for Information Interchange, which has been around since I think at least the 60s, where there is a 7-bit binary pattern, a unique 7-bit binary pattern assigned to every character on your keyboard, as well as some non-visible characters. And I think we showed this to you in 177 as well. So if you look over here in this table, these are all the characters that we need to assign an ASCII code to. You have all of your letters, uppercase and lowercase. And you have, all your numbers as well, or I should really say numerical digits, your space, all your punctuation, etc. And then some non-visible characters as well here, which are, many of these are leftovers from, old obsolete technology in the past. I think I mentioned in 177 that, when I was in your position programming and we were programming our first microprocessor or something, they taught us ASCII. As soon as everybody figured out how to do that, where is it? I can't find it here, but somewhere in here there's a bell. I can't see it offhand now. But in any case, oh, here it is, the audible signal. I still remember, in one of my programming labs where we were looking at ASCII codes, and all of a sudden everybody's computer started ringing because everybody figured out how to send this ASCII code to the processor. Okay, so you've seen that before. So with ASCII, there is a unique 7-bit pattern. For instance, this represents the uppercase A, this represents the lowercase a. And you have the full table in your textbook. Okay, well, as computers started getting more popular in the 70s and especially the 80s, and started to be used all around the world, it soon became obvious that we needed to represent other characters because people who didn't use English as their language also wanted to, for instance, be able to store the characters of their own language in a computer. And if their language did not use the Latin characters, A to Z, well, they were kind of out of luck. So back then, an organization started which created what we call Unicode, okay, which is still around today. You can look it up online, unicode.org, I think is their website. And it's basically the same thing as an ASCII code, and in fact, the ASCII representation, 7-bit representations for all of these standard characters are part of Unicode. They're just a subset. Unicode now has unique binary, and obviously they have to be bigger than 7 bits because there's so many different characters out there. Every one of these characters will have a unique, I forget how many bits are in them now, let's say 20. Let's say that's the number. Every character in the world now has a unique 20-bit pattern. So there's greater than 100,000 characters already represented. And it's not characters anymore, but emojis are part of Unicode as well. Every emoji that you send in a text or whatnot has a unique binary pattern that is part of Unicode. Okay, so now that allows people to use all sorts of languages in computers and store different types of characters and even graphics now. Okay, so that's characters and etc. ASCII and Unicode. All right, well, so far we've only, the numbers we've been talking about have been unsigned integers. You know, for instance, positive. When we're converting between decimal and binary or just looking at binary numbers, we're just assuming they're unsigned positive numbers. Obviously, we need to represent signed numbers in a computer. We have positive and negative numbers. Well, so how can we do that? Well, over the years, three different solutions have been proposed, and pretty much everybody now uses solution number 3. But we'll look at solution number 1 and 2 just so that we recognize them. Solution number 1 is really straightforward. It just says, well, there's only two there's only two possible signs a number can have, positive and negative. So therefore, why don't we just add a bit to the most significant end of a number, let's say a binary number, and let's say if that bit is 0, then the number that follows is positive. If that bit is 1, well, then the number that follows is negative. Very straightforward, very simple to implement in a computer, okay? So for instance, if we're trying to represent the decimal number positive 27 in binary, okay, well then the digits here in blue would be the magnitude 27. So 1 plus 2 plus 8 plus 16 would give you 27. And then this most significant bit here would be the sign bit. And since this is supposed to be positive 27, we make it 0. Negative 27 will be the exact same bit pattern. The magnitude bits are still the same. They correspond to 27. But we just make the sign bit a 1, indicating it's a negative number. Okay, so very, very simple and easy to implement. We'll talk about why it's not so good in a little bit. Solution number 2 came along, which said, well, we're going to instead we're going to use what's called the ones complement system, which means that if the number is negative, we're just going to complement. That means invert or negate every bit in the number itself. So let's again start with positive 27, which looks like this. If we want to write negative 27, we just invert every bit. So this 0 becomes a 1, a 1, a 1, a 0, 0, 1, 0, 0. Okay? And again, the most significant bit can be interpreted as the sign bit. In this case, 0 would mean it's a positive number, positive 27. This 1 would be a negative number, negative 27. Well, how would we know that this corresponds to negative 27? This magnitude no longer equals 27. It would equal 1, 2, 4, 8, 16, 32, and 64 is 96, 100, I guess. Well, you just negate all the bits again and you get 27 back. So if you're given a number in the ones complement system and you look at the most significant bit, you see it's a 1, you know it's a negative number first of all. In order to figure out which negative number, you just invert all the bits to get this. And then add up the placeholder values and you got 27, so you know it's negative 27. Okay, so that's the ones complement solution. Again, for reasons we'll talk about a little bit in a moment, that still wasn't enough, so they went to a third solution, and this is the solution pretty much used by every computer these days. It's the twos complement system. And the twos complement system is It's basically the same as the ones complement system. If you start with if it's negative 27 we want to express, we start with positive 27. So we write the bits, the binary number 27, the most significant sign bit, which would be 0. We then invert all the bits, just like we do with ones complement. So at this point we have the ones complement number. Okay? And then to make it 2's complement, we just add 1. So if you add 1 to this, that just changes the last digit here, obviously, from 0 to 1. And now we have the 2's complement representation of negative 27. Excuse me. Okay, so same thing with ones complement. If you're given a binary pattern like this and you're told it's a 2's complement binary number, you look at the most significant bit, you see it's a 1, you know it's a negative number. Well, which negative number? Well, you invert all the bits, so 0, 0, 0, 1, 0, 1, 0, 1, and then you add 1 to it. So 1 plus 1 is 0, carry the 1, gives us 1, 1, 0, 1, 0, 0, 0, which is the, what did I do wrong? I should get the same number back again. 1, 1, 0, 0, 1, 0, 1. I inverted the first 4 bits, but not the last 4 bits. Let's try that again. Okay, so let's invert the bits again. As we go from, we start with this and invert all the bits. So 0, 0, 0, 1, 1, 0, 1, 0. And add the 1. So 1 plus 0 is 1, and then all the rest are just the same. Okay, and we end up with the same number we started with. So we know that it's negative 27. Okay, so this seems kind of weird. Why would we, what's so special about the 2's complement system? Well, the reason it's used is it's actually the most efficient to be used in, to be implemented in hardware. Okay, and why? Let me just double check. 1110, yeah, and then here. Oh no, this is the ones complement here. So 111, all zeros except for that one. It's okay, because it's, that's not what I want to do. Is that, well, first let's look at the all of the signed numbers that we, using the 3 different types of signed representations for these binary numbers here, these 4-bit binary numbers. And you'll notice that these are not written in ascending order. 0 starts here, 0, 1, 2, 3, 4, 5, 6, 7. If we interpret these as unsigned binary numbers, 8, 9, 10, 11, 12, 13, 14, 15. But we've written them in this way so that because when we interpret them as signed binary numbers, we get orders that make a little bit more sense when we write them out like this. Okay, so here are our 3 different ways of representing a signed number. Sign in magnitude, which simply means that the first bit, which is the sign bit, is, you know, these are all positive numbers, these are all negative numbers, this is 0, positive 1, positive 2, 3, 4, 5, 6, 7. This one would be negative 0, since the magnitude is 0, the sign is negative. We get a negative 0, which is one reason this is not a good way of doing it. We actually have 2 different binary patterns that both mean 0. And then negative, pardon me. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, and negative 7. Okay, so that's sign and magnitude. So it doesn't look too bad, except that we've got 2 zeros here. If we go to ones complement, it's not a whole lot better. We still have 2 values for 0, a positive 0 and a negative 0. Right? Because if you take this 111 here, and you say, okay, well, that's a ones complement number. It's a negative number because the first bit is 0. Which negative number is it? Well, you convert, or you flip all those bits, you invert them, it's negative 0. So we still have this problem of 2 zeros. Finally, 2's complement, we get rid of the 2 zeros. There is only one value for 0, and that is what we would expect, 0, 0, 0, 0. So that gets rid of one problem. The other problem is, as we'll see in a minute, 1's complement has some problems when we're adding and subtracting numbers. 2's complement, we don't have the same problem. So sign and magnitude is never really used, neither is 1's complement. 2's complement is almost up here. Typo. 1's here. That would be here, negative 0. When it's all 1's, it's negative 0. If you look at these 2's complement values, one reason it works well in hardware is because as you're moving this way in the numbers, obviously these binary numbers are changing like this. Maybe let's go the other way. Let's say we're going this way. You might think that, well, this doesn't really make sense. You're going 7, 6, 5, 4, 3, 2, 1, 0, 8, 7, negative 8, negative 7. Shouldn't it go this way? We're used to writing numbers like this, right? But again, the order of these numbers is based on the order we chose to write these binary numbers. And the good thing about 2's complement is that as we move, say, from this direction, this is the smallest negative number we can write with 4 bits in the 2's complement system, right? Pardon me. I think I better stop. Okay, I'm not going to explain this anymore. We're out of time. We talked about why 2's complement is. You're talking about 1's complement?
Yeah. So, if this is a positive A, it should be 1, 000, right?
But you can, because this bit is the sign bit.
Okay.
This bit.
So we need to sign. How can we just sign like positive A? So it should be 0, 0, 0,
Well,
0 and 1.
Right. You would need more bits in your number. You would need at least you'd need at least a 5-bit number. Or let's more realistic, it would be an 8-bit number. So for instance, 1, 2, 4, 8. So if you had an 8-bit word, that would be positive 8.
Okay, I see.
Yeah.
Right. Thank you.
Yeah. Okay. All right. See you on Friday, everyone. Was used. Okay. Well, let's just look a little bit more at the problem with 1's complement. Oh, and I'm sorry about my throat. Okay, so when you're adding 1's complement numbers, there's nothing wrong. Everything works great. And these are just 1-bit binary numbers. When you add them, everything works as it should. You add from right to left, and 1 plus 1 is 2, which is this in binary. So 1 plus 1 is 0. Carry the 1 gives us that. That's all great. But when we're subtracting numbers in the 1's complement system, things don't work out quite so good. When we subtract, what we usually do is we add the negative. So if we want to subtract 27 from 27, what we do is we add 27 to negative 27. So in the 1's complement system, this is the binary pattern for negative 27, which should be the same pattern as we have. think there might be 1, 1, 1, all zeros, right, except for that one. So this is the ones complement representation for negative 27. So 27 minus 27 in ones complement would be plus 27 plus negative 27, which results in this, which is got here. Okay, so in one sense that's okay, although it's not what we would really like, which is 0, 0, 0, 0, 0. There's two values of 0. We also have a problem. For instance, let's look at these more simple examples down here where we're subtracting 6 from 5. So 5 minus 6 or plus 5 plus negative 6. So again, if we represent plus 5 in one's complement and negative 6 in one's complement, we add those together, which is the equivalent of 5 minus 6. We get this value. Okay? So we went from 4 binary digits to 5. So there was a carry out of 0. Right? If I write this out explicitly, 0, 1, 0, 1, and 1, 0, 0, 1. 1 plus 1 is 0, carry the 1. 1 plus 0 plus 0 is 1. 1 plus 0 is 1. 0 plus 1 is 1. There is no carry out, or we could say the carry out is 0. Okay? The result being 1, 1, 1, 0 is correct. It's the ones complement version of negative 1. Okay? We can see that the sign bit is 1, meaning it's a negative number. Which negative number? We'll invert all these bits to make it, and we would get 0, 0, 0, 1. So it would be negative 1, which is what correct for 5 minus 6, or 5 plus negative 6. So that's fine. Well, what about 7 plus negative 3, or 7 minus 3? Well, in that case, take our 7s, which is 0, 1, 1, 1. We take our negative 3, which in one's complement is 1, 1, 0, 0. And we get 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 0, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. So we get a 4-bit pattern, 0, 0, 1, 1, which is not correct. Okay? Obviously, 7 plus negative 3, or 7 minus 3, is equal to 4, and what we end up with is 3. Okay, this 4-bit binary number has the value of 3. So it's wrong, but all we have to do is add 1 to it to get the correct number of 4. Okay, so, but the carry bit was 1. So you can use one's complement, it just requires a correction step. Okay, if when you add or subtract, if you're subtracting or adding a negative, and the carry bit is a 0, well then your result is correct. Okay? If, however, when you subtract two numbers in one's complement and the carry out is a 1, well then you have to add 1 to the result to get the correct answer. Okay, so it's not the end of the world. You can use it, but you need this correction cycle. And it's relatively straightforward to implement on a computer. Processors are designed to monitor what this carry-out bit is. If it's a 0, it knows it's fine. If it's a 1, it knows it has to add 1. Okay? So there's these two problems with the ones complement system. First of all, there's two values for 0. And second of all, you need this correction step if you're subtracting two numbers. Here, superior and
just assign like positive 8 or positive 128.
So that's what. Okay, well, what about for 2's complement? Well, the 2's complement is good. First of all, there's only a single unique binary pattern for for 0. There's not two of them. And second of all, we don't need this correction step when we're subtracting two numbers in 2's complement. Okay, subtraction and addition, no problem. There's no correction cycle needed. So, for instance, if we're subtracting 17 from 27, So this is the, this is the value for positive 27. This is the binary value for positive 17. And if we subtract them, well, 1 minus 1 is 0, 1 minus 0 is 1, 0 minus 0 is 0, 1 minus 0 is 1, 1 minus 1 is 0, 0, 0, 0. We get positive 10, which is what we expect. Now, if we were to do this in a computer with 2's complement, we would add the negative. Okay, so again, 27 is like this. The 2's complement version for a positive number is the same as the unsigned value. To find the 2's complement for 17, we would have to, I'll do it up here, we invert all the bits, so 1, 1, 0, 1, 1, 1, 0, and we add 1 to get 1, 1, 1, 1, 0, 1, 1, 1. Okay, so that is our 2's complement representation of the number negative 17. Okay, and now we add them. Well, when you add these, you get 1 plus 1 is 0, carry the 1. And now 1 plus 1 plus 1 is 3, which is 1, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 3, which is 1, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. And 1 plus 1 is 0, carry the 1. But we can ignore the carry out. We don't need to look at it in 2's complement, so we just ignore it. And we can see that what we get as a result here is what we're expecting, right? This is the binary, it's a positive number, 1, 2, 4, 8, this is positive 10, which is what we would expect to get from 27 plus negative 17. Okay, so 2's complement doesn't suffer from the same problems as 1's complement, which is 2 values for 0, as well as this correction cycle that is needed when you're subtracting numbers. You don't have to look at the carry bit when you're subtracting in 2's complement. You can just ignore it, whereas in 1's complement you need to look at it in order to get the correct result. Okay, so in a sort of those are the main reasons that we use 2's complement. Note that the ranges for 8-bit unsigned and signed numbers are different. Yes, if we've got an 8-bit unsigned, that obviously they're all 0 numbers from 0 to plus 25. With 8 bits 2's complement, we go from negative 128 to positive 127. It's still the same number of numbers, but half of them are negative, half of them are positive because of the sign bit. Okay, we're almost done for today. Maybe go just to implement what's next. Well, let's end with this. Why does the 2's complement number system work so well? It's because, in a nutshell, it's because it does mod 16 arithmetic really well. Okay, and in the time we got remaining, I don't think I'm going to be able to explain this. If in hardware, if you're interested more in this and what I mean by mod 16, there's a page in the textbook. I think it's in the reading at the end of this chapter, especially about this wheel here and how it works. It's not critical for our understanding, but if you're interested more in why 2's complement works so well, feel free to look at that in the textbook. Okay, but we'll end there and we'll read. Continue on, we go and floating point numbers and then carry on Friday. Okay? All right, sorry about my voice and that it wasn't so well. Tian Cheng, go ahead.
Yeah, I have some problem for the first complement there.
But you can talk about these tomorrow, and then we'll talk about if you go here, forget now. You're ready at the end of this chapter. Yeah, probably somewhere in section, or it might be in chapter 1, maybe.